allow me to ask you a question. If you could visit anywhere on the moon, where would you go? Look across the crater-pocked, dust-strewn landscape. There are mountains and craters here, scientific marvels and mysteries cloaked in pitch-black shadows. But without the proper map, it would be easy to miss some of the wondrous features of our closest celestial neighbour. Fortunately for us, for a decade and a half, the LRO, or Lunar Reconnaissance Orbiter, has been compiling just such a map. In ways never seen before, it has imaged the features of the lunar terrain, helping scientists learn more about the moon's ever-evolving surface and the processes that govern it. With over 8 billion different measurements taken, its complex analysis has made the moon the most thoroughly measured of any other non-Earth object in the solar system, and has given us the tools we need to perhaps one day set up permanent bases there. What did it find? And given that the moon is an object you've likely seen thousands of times in the night sky throughout the course of your life, it's time to find out, how well do you really know it? I'm Alex McColgan and you're watching Astrum, and in this LRO Supercut, we will explore some of the most fascinating discoveries and landmarks imaged by the LRO throughout its mission to the moon to date. The LRO has been scanning the moon's surface since 2009. It's equipped with a powerful camera capable of taking high-definition photos, which it sends to NASA's Data Planetary System. The LRO can send up to 155 gigabytes of data per day, or 55 terabytes per year. By comparison, New Horizons took a full 2 years to transmit the data from its one Pluto flyby. Although the LRO was launched over a decade ago, it's still operational, and we are constantly learning new things about the lunar surface thanks to its high-powered camera and topographic mapping capabilities. Let's see that camera in action. We'll start with a place rich in incredible contrast, Jackson Crater. This oblique angle shot of Jackson Crater is sadly not visible to us on Earth, as it is on the far side of the moon. A bit like Tycho Crater on the near side of the moon, when it formed, it created a ray system stretching over 1,000 kilometers. Ray systems form when particularly fine material is ejected far beyond the crater rim, although their formation is still being studied. Jackson Crater itself is about 70 kilometers in diameter, and due to its size, it is a complex crater, as can be seen by its terraced walls and uplift in the central region. This crater is actually tilted. The east side of the crater is 6,000 meters in elevation, and the west side is only 3,000 meters high. The base of the crater has an elevation of 1,000 meters, and the peak comprises of material that was pushed up from another 1,000 meters down. Some of the dark patches you see along the walls are shadows due to the sun's angle in the sky, but there are also sections of darker materials compared to the predominantly lighter colored ground, although it's not as light as this image would have you think. Your viewing angle and the angle of the sun play a big role in how contrasts appear on the lunar surface. Focus here on the central peak in this image. We'll now switch to a top-down perspective of this same peak, taken at a different time of the lunar day. Suddenly, the crater basin and the tip of the mountain appear much darker than before. But a side-by-side comparison does show how the differences in contrast can be seen in both pictures. And that's not the only optical illusion the moon can trick you with. Have a close look at this image. What does it appear like to you? Are these regions of inverted bubbles? Or are these sections actually rising higher than the wiggly textured material surrounding them? Well, for the longest time, I could only see it's inverted. But maybe if you look around the image, suddenly it will switch perspectives for you. What type of image did you see first? Are you like me and need proof it's not actually inverted? Well, have a look at the same region but from a different angle. Seeing it like this makes me wonder how I could have seen anything else. This is a small region on the Moon called Inner. It's only 2 to 3 kilometers wide and 64 meters deep, and no one really knows how something like this formed. It's one of several similar regions on the Moon, although this one is the most prominent. To a certain degree, a similar optical illusion can happen with small craters. Do you see domes here, or craters? Sometimes rotating the picture can help get the right perspective. That's why the LRO is so useful in my opinion. Not only do we get top-down views, but oblique perspectives too. Moving on to another unusual lunar region, let's have a look at Komarov crater. This crater would be pretty normal by lunar standards were it not for the fact that it has huge fracture lines running across the base. Komarov crater itself is even bigger than Jackson crater at 95 kilometers in diameter, meaning these are up to 500 meters deep and 2.5 kilometers wide. It is believed that 2.6 billion years ago, magma built up under the crater, causing large amounts of pressure to fracture the crust, although it appears that the magma never made it to the surface, meaning the fractures were never filled in, and it remained like that ever since. But although it didn't happen in this instance, there are examples on the Moon of magma breaking through and pooling on the surface. One such example can be found west of Plato crater, a large 100-kilometer wide crater seen towards the north of the Moon, visible with a telescope or binoculars on Earth. This image has a few rather spectacular points of interest to see, the obvious one being this channel which cuts through the ground. This section here is a lava vent, back when the Moon was a lot more geologically active. Running out of the vent, in a southwesterly direction, is something known as a rimma or a rill. These are channels cut out by lava melting and eroding its way down the slope, kind of like a river on Earth. To the east in this image, we see the crater rim of Plato. Plato itself was likely filled with lava at some point, as the base is darker and smoother than the regions northwards. However, in this image, we can see that a huge section of crust has collapsed down from the crater wall, creating a 24-kilometer wide slump block. In other words, this section was once connected to the higher plane. However, it has since collapsed under its own weight, breaking away and falling somewhat into the crater. For now, let's have a look at one more crater. This breathtaking view is from the Apollo 15 mission overlooking Aristarchus crater. Aristarchus is seen towards the northwest of the Moon, and although Aristarchus is only 40 kilometers across, it's bright enough to be seen with the naked eye. From Apollo's viewpoint, we can see a really wide angled perspective of the crater. Surrounding it are more rills and lava vents, and a small ray system can be seen extending away from the center. From this angle, with the shadow extruding out from the rim, you get a sense of how deep this crater is. This complex crater has prominent crater walls, however, the uplift found in the center seems pretty small. From LRO's perspective, we have a much higher resolution view of Aristarchus again, and we can have a close examination of the walls and crater base. The walls are similar in appearance to Jackson crater. However, looking at the peak towards the crater's center reveals some major differences. Not only is the peak much smaller, it also has a banded pattern, exposing layers in the crust that would have otherwise been hidden hundreds of meters down. The base of the crater was also likely to have formed from molten lava, rock melted by the impactor. Fracture lines from rapid cooling are evident all over, and looking at where the walls meet the crater base, you can easily imagine how this base was once a liquid. For a place that's so grey, colour on the Moon can tell us a lot. This area is known as Mons Carpatus, and what's immediately apparent here are the variations in contrast again. Generally speaking, looking at darker regions on the Moon indicates older material, but it also indicates what the material is composed of. The darkest regions in this image are thought to have formed from explosive volcanic activity over 3 billion years ago. Lava would have also flowed down through valleys like these ones. Also sprinkling the surface are white dots. These are small impact craters and appear white as they are a lot more fresh than the surrounding regions, and space weathering hasn't had an opportunity to darken them yet. Now, the Lunar Reconnaissance Orbiter, unlike the Mars Reconnaissance Orbiter, has a special ability to be able to take photos from an angle as well as from a top-down perspective. This means we are able to view the mountains of the moon as if from the cockpit of a plane, which gives us a better sense of height and scale. Although our sense of scale is already seriously messed up, as on Earth we have visual clues to help us judge how high or how far away something is. For instance, we can tell the background here must be tens of kilometers away because the atmosphere makes the mountains quite hazy. Also, we can see the town, some trees, all of which help us know roughly how big the object is that we're looking at. But on the moon, we don't have any of that. No trees, no atmosphere, no towns. Just looking at this image, how big would you say this mountain is? How wide is the foreground in this image? It would be fun to see your guesses in the comments. But, perhaps surprisingly, the foreground of this image is about 15 kilometers across, and the foreground mountain is nearly 7 kilometers tall. These two peaks at the back are a massive 200 kilometers away and roughly 4,500 meters tall. Surprisingly, these peaks aren't named like they would be if they were on Earth at that size. The best way to kind of get a sense of scale for these images is to use this amazing tool NASA has released called QuickMap, where you can see the moon under various filters, including a topographical map. I'll leave a link in the description below if you want to check it out. Here's the mountain in the foreground of the image, and here are the background peaks. You'll also notice that these peaks are found around the rim of a crater. Pretty much all of the mountains we will look at today can be found either on the rims or centers of craters, including these ones found in the famous Copernicus crater. When craters form, we all tend to think of the circle they create, but big craters often have uplift in the center. Surprisingly enough, this is not predominantly due to an effect like a water drop impacting a pool of water or elastic rebound, where the center shoots up again after impact. That only happens with material with elastic strength trying to return to its original shape. Rather, craters have uplift in the center due to the surface material attempting to revert to a gravitational equilibrium. Copernicus crater can easily be seen on the surface of the moon by an amateur telescope, and as a result is one of the moon's most viewed features from the ground. These mountains in the center look impressive, but they only rise about 1,000 meters above the crater floor. Zooming out a bit, and you can see how dwarfed they are by the surrounding crater walls, reaching 4,000 meters above the crater floor. Here's the crater from another angle, and one thing you'll notice is that the basin of this crater is lumpy but comparatively flat. This is because after the massive impact that caused this 100-kilometer wide crater, the floor was lava, which eventually solidified. Moving on to a new location on the moon, and we come to the Apennine Mountains, an impressive range of 3 to 5 kilometer high mountains found at the rim of one of the biggest impact craters in the whole solar system, the Imbrium Basin, or Mare Imbrium. These mountains look interesting next to this mare, or solidified lava plain, and this rill, kind of like a gorge found on the moon. But apart from being a very interesting view, there's something special about this place. It is in fact where the Apollo 15 mission landed in 1971, which means there is also a ground perspective to these mountains. Here is the lunar module with these same mountains in the background. And here it looks like they are so close, but remember, our perception of things is skewed. These actually rise about 5 kilometers high from the plane the camera is on, higher than the Himalayan front above the Nepalese and Indian plains on Earth. Astronauts also investigated the rill using their lunar rover. This rill actually drops down 380 meters. Rills are a bit of a mystery, as it isn't clear why they are there. One leading theory is that they are the exposed or collapsed magma tunnels underneath the surface of the moon back when it was more geologically active. From the perspective of the Lunar Reconnaissance Orbiter, the tracks left by the rover can still be seen today, as there is no wind on the moon to cover up the tracks with dust. So even though the Apollo mission happened about 40 years before this photo was taken, the remains can still be seen in pristine detail. It wouldn't be right to talk about some of the highest points on the moon without talking about the highest point. Sadly, it doesn't look too impressive, as it has a really shallow gradient, only 3 degrees. It's near one of the biggest impact craters in the whole solar system, and certainly the biggest on the moon, the Aitken Basin, which likely formed 4 billion years ago. This is where the Chang'e 4 Chinese mission landed back in 2019, which impressively LRO was able to image. As you can see, this crater is huge, 2,500 kilometers across, and would have created a lot of ejecta. This ejecta piled up all around the crater, including what is now known as the highest point on the moon. The basin was likely caused by a low velocity impact with an object 200 kilometers in diameter, and would have been at a sharp angle as the ejecta was flung mainly in one direction. Interestingly, the lowest point on the moon is not so far away from the highest point. The lowest point, found at the bottom of a crater within the basin, is minus 9,106 meters, and the highest point is taller than Everest at 10,786 meters. Just as a side note for all those of you that are curious, these heights come from comparing the average radius of the moon with the elevation of that point. As you can see, the surface of the moon is littered with craters. It doesn't matter where you are on the moon, there'll be craters of various sizes. This implies that the surface is old and hasn't been renewed by lava eruptions from the mantle anytime recently. The most recent eruption thought to have happened 1.2 billion years ago. There are an estimated 300,000 impact craters over 1 kilometer across on the surface of the moon facing us, and millions more smaller than that, like the ones you are currently looking at. The moon can have such small craters because it has no atmosphere, meaning every meteorite heading for the moon will hit its surface. On Earth, most meteors burn up in the atmosphere. Just imagine how many shooting stars there are each night. Were it not for Earth's atmosphere, every one of them would impact our surface too. What's interesting about each crater you see here is that you can roughly estimate how old a crater is by how eroded it is. Craters which appear very smooth are much older than craters with lighter substances surrounding them, with sharp and defined edges. The bright patches haven't had so long to have a weathering effect happen on them. But weathering on the moon? How can that be? Well, this weathering is not caused by water or air, but rather by tiny micrometeor impacts and intense radiation from the sun, which dull the thin outer layer of the moon. If we speed along to the end of this image, we can see a relatively fresh crater only a few hundred meters across. Using LRO's narrow angle camera, we can see a close-up view of the effects of such an impact on the lunar surface. These linear patterns are the effects of the ejecta from the impact. Finer dust would have been blown across the surface with some force. Larger boulders not quite making it as far, although leaving a trail from where they rolled away from the impact. The crater itself isn't super clear in this image due to the time in the lunar day this was taken, the sun close to the horizon, casting long shadows across the surface, although you can still see fresh exposed material along the crater wall. Comparing this to an old crater, here you can see a much smoother and darker looking crater, although still brighter than the heavily weathered surface in the surrounding area. What I like about this image though is that zooming in, you can see some ejecta that landed from another impact off the image. Here's a boulder that landed on the crater wall and then rolled halfway down. The only thing with these top-down perspectives is that you don't get a great concept of depth in the image. How shallow or deep can craters get? Luckily, the LRO doesn't just scan the surface, but can take more oblique shots of the moon too, which can definitely help us appreciate depth. Look at this fantastic image. The crater is around 21 kilometers across, and it has some fascinating details all around it. Again, we can see the trails left by huge boulders rolling down the slopes, and very bright walls implying it is a young crater, yet darker material at the base. The contrasts are really quite vivid, and it almost looks like some parts could have been liquid at some point. The impact would have initially melted the rock into lava, which flowed to the bottom, collecting in pools which have since solidified. The impactor was likely 2 kilometers in diameter and hit the moon 10 times faster than the speed of a bullet. That would have been some collision indeed. Another great image I have to show you is this. A crater 10 kilometers across. What's special about this one is its interestingly raised rim. This is another example of rock melting from the impact, but rather, this time, slopping beyond the rim and flowing down before solidifying again. If we look closely around the crater, you can also see ejecta scattered across the surface, disturbing the ground and leaving brighter patches exposed. See? Once you know what you are looking at, even the moon becomes very interesting. But these have been very pristine craters. What if a meteor lands somewhere a little less conventional? Here is a crater within a crater. The impactor hit the wall of the larger crater, meaning it has quite an unusual shape. Although from a top-down perspective, it still looks quite circular. Just as a side note, this image is a true color image of the moon. Most other images of the moon are taken in black and white to save bandwidth. Astronomers prefer resolution over color, although the lowest resolution camera on the LRO is capable of color, and this is an example of it. But certain craters can be unconventional in other ways too. There's a little understood phenomena on the moon that scientists have so far struggled to explain, and that is cold patches found on the moon after the sun goes down. So far, we have really only focused on the cameras equipped on the LRO, but it has a host of other instruments on board, including the Diviner Lunar Radiometer experiment, which has mapped the moon's surface temperatures. There are 2,000 points on the moon that cool down more than the surrounding areas when the sun goes down. When the sun rises on the spots again, they normalize their temperature and quickly blend in with the background. The only thing these spots seem to have in common? They are always found around young craters, no smaller than 50 meters and no bigger than 2.3 kilometers. But the spots themselves are much larger than the craters. Here is a heat map of the crater I was just showing you. White is the hottest parts of the image, blue is the coolest. As you can see, a large cool region surrounds the young crater. There is an ongoing investigation to find out the cause. What do you think it could be? Speaking of cool areas, let's jump now to one of the coldest locations in the solar system. It's an image I personally find breathtaking. This crater, found near the south pole of the moon, is almost always in shadow. The sun never rises high above the horizon here, meaning only the peaks of the crater stick out enough to be enveloped in light. What you are left with is a stunning contrast, almost like the yin and yang symbol. This is certainly my new desktop background image. But this region isn't just an eerily beautiful place, but it is actually one of the candidates for the future Artemis mission to the moon. The lunar South Pole is of particular importance to future human missions, as there is thought to be millions of tons of water ice to be found in this region at the bottom of craters like this, forever protected from the sun's rays. If there is to be a future colony on the moon, this is roughly where it would be located. While massive craters, pristine mountains, and shadow-dappled landscapes are all eerily beautiful to look at, a large part of why the images taken by LRO are so important is because of how well it advances our scientific understanding of the moon's formation. Let's take a look at one of these images. At first glance, it may seem unremarkable, but a deeper look tells a different story. See those two large, round depressions? Those are impact craters, much like countless others that blanket the lunar surface. But if we zoom out, we see that these craters are located on an unusual dome-like structure. This is Mons Gruithuisen Gamma. Look how the western side of the dome appears lighter where the sun's light is reflecting off its steep slope. By contrast, the western sides of the craters are plunged into shadow due to their low elevation. Shadows on the moon are so dark compared to Earth due to the absence of Rayleigh scattering in the atmosphere. The moon has no atmosphere, so the only light that reaches shadowy regions are reflections from the lunar surface itself, which isn't actually that reflective. It is generally very dark, with an average albedo of 0.12, about as dark as wet soil. Directly to the dome's east is a dark shadow cast by the dome itself, and it gives you a sense of how tall it is. The dome is towering, with a slope of up to 20 degrees and rising 1,500 meters above the lunar surface. With a diameter of 20 kilometers, it's equivalent to the metro area of a mid-sized city. That's pretty massive. Zooming out further, we see that the dome is surrounded by darker and much flatter terrain. This plain, or mare, is the result of basaltic lava flows that flooded the topographic lows around 4 billion years ago, resulting in the even surface you see now. Think of it like ice cream dripping into the crevices of a wafer cone. Zooming out further still, we see a second dome located to the southeast of Mons Gruithuisen Gamma. This is Mons Gruithuisen Delta, and it's even bigger than its cousin, towering 1,800 meters above the surrounding surface and spanning 27 kilometers in diameter. The dark basalt plain that surrounds both domes is part of a vast mare we saw earlier, Oceanus Procellarum, or Ocean of Storms, which covers a full 10.5% of the lunar surface. I don't know about you, but I think ocean is a fitting word. The domes look a bit like islands. It is believed that the Gruithuisen domes, like the Oceanus Procellarum, were formed by ancient lava flows. But why did they leave these unusual structures? Believe it or not, there may be clues here on Earth. This is Mount St. Helens, an active stratovolcano located in America's Pacific Northwest. Maybe you can see where I'm going with this. As you can see, it's shaped a bit like a dome. Stratovolcanoes like this one are the result of pyroclastic flows of silica-rich materials like rhyolite, dacite, and andesite. Once expelled from the Earth's crust, these high viscosity lavas move slowly as they cool, hardening into dome-like or conical formations over time. We suspect that the Gruithuisen domes, like terrestrial stratovolcanoes, are made of highly silicic material, and recent thermal measurements by the LRO's Diviner instrument support this theory, suggesting the domes are compositionally different from their surrounding plane. So, unlike the moon's basalt lavas, which settled into smooth, low-lying surfaces, these more viscous, silica-rich lavas extruded slowly, like thick molasses, eventually cooling and leaving the massive domes you see now. But here's where it gets strange. On Earth, stratovolcanoes like Mount St. Helens are a unique product of water and plate tectonics. At the convergence of two tectonic plates, a subduction zone can occur where colder and denser material from an oceanic plate is thrust under the less dense plate and back into the Earth's blazing hot mantle. The remelted material results in silica-rich magmas like rhyolite and dacite, which then rise. But unlike here on Earth, neither liquid water nor plate tectonics are present on the moon. So how did these silica-rich magmas form? We're not sure. One explanation suggests that when lunar magma had nearly cooled and crystallized, it left a residual liquid that could have been extremely rich in silica. The problem, however, is that this process, known as fractional crystallization, would produce only small quantities of silicic material, which wouldn't be nearly enough to explain a massive 27-kilometer Goliath like Mons Groothuizen Delta. A second model suggests that silicic material formed when basalt magma rose upward, causing rocks on the lunar surface to partially melt and form rhyolites and dacites. If this were indeed the case, then the Groothuizen domes should be nearly the same age as the surrounding basalt plain. We don't know if this is true yet, but future research could shed light on both the chronology and composition of these mysterious structures. To me, the most exciting part is that we may be just a few years away from getting an answer. NASA plans to send a commercial Lunar Payload Services rover to this region in 2025. This mission will explore the moon's surface and collect rock samples that should shed light, not just on the mysterious Groothuizen domes, but on lunar volcanism in general. And high-definition images taken by the LRO, like the ones we've been studying today, will provide NASA with crucial information for selecting a safe and navigable landing spot. It's exciting to imagine how this mission will add to our current understanding of the moon, with on-the-ground imaging and rock samples. And honestly, I can't wait. Which of the two theories to explain the formation of the Groothuizen domes do you think sounds more plausible? I'd love to hear your ideas in the comments. As you can see by now, not everything on the moon is fully understood. For example, let's turn to this innocuous unnamed crater. As you can see, there are plenty of tiny craters within it. And this crater is within another crater again. Maybe you can see where I'm going with this. Zooming out, not only are these craters in another crater, but apparently they are contained within two very nicely aligned craters. Or is that really what this is? Well, we aren't sure. Both of these craters are named as one, the Belle E crater. This peculiar type of crater is known as a donut or concentric crater. It is possible that they are the result of two impactors aligning up nicely, but further investigation suggests otherwise. If they were the result of chance collisions, then there should be a random distribution of concentric craters around the surface of the moon. However, that is not the case. Have a look at this. The population of concentric craters actually clump up around certain areas, especially around the edge of this region of the moon here, called Oceanus Procellarum. Another factor to consider is that most of these craters are of similar ages. Looking for clues in the crater itself also reveals something interesting. This outer crater should be around twice as deep as it currently is when comparing it to other similar sized craters around the moon. Now, while a few concentric craters on the moon will certainly be the result of double impacts, the location, age, and depth of most craters means that something else must be at play. One theory is that some of these impacts occurred during a time when the surface of the moon in this region was in a state in between solid and liquid, with a consistency similar to cool lava or honey. As the impact happened, it caused ripples which propagated outwards, but then stopped and never smoothed off until it was fully cooled and frozen in place. Although this is seen as an outside possibility. The most likely theory is that when the moon was more geologically active, craters in the region were pushed up from beneath by magma trying to escape onto the surface. This would explain the shallowness of the crater, and why we see concentric craters mainly around specific points on the moon. However, while this is the best theory we have at the moment, we don't know for sure. What do you think it could be? Now, apart from the occasional meteor, You probably think the surface of the moon barely changes at all. And while you are mostly right with that, we have found evidence that material does move on the moon occasionally. See if you can spot what I'm talking about in this image here as I pan across. This is the edge of a large 32-kilometer wide crater known as Kepler crater, and what you may notice along the crater wall is evidence that landslides have occurred here, with the dark material apparently having fallen down the slope. Let's have a closer look at what's going on by zooming in on the most prominent of the landslides in this crater. The material seems to originate from box canyons towards the top of the crater rim. The material coming down here is clearly very fine, certainly less than a meter across, as no individual rocks can be resolved within the slide. However, the largest rocks that got dislodged seem to have all made it to the bottom of the crater floor. What's interesting is that the main mass of the slide seems to actually be made up of many smaller slide masses. Look at these individual trails here. So it probably didn't all happen at once, but is happening over time. The slides were likely triggered by tiny meteors striking the crater wall. These tiny impacts and the subsequent landslides round off the edges of the crater, which is why the oldest types of crater on the moon look so smooth compared to the freshest craters. Here's another puzzle to try and solve. Here we have the remarkable Messier crater. Typically, craters are round, but not Messier crater. It is elongated with a slit for a crater floor. What is going on here? The mystery continues if you zoom out a bit. Directly next to Messier crater are two more craters. The one on the left seems much older than the other, as it seems to have been weathered away compared to the fresh impact crater on the right. Did the newer crater just so happen to cover an older one? But let's zoom out again. What other clues can we see? Actually, a big clue are these lines coming away from the crater. These are called rays, and they reveal the direction the debris fell after the impact. On rounded craters, debris can go in all directions, like the ones that originate from Tycho crater. However, here, debris goes in three distinct directions: north and southward from this crater, and only westward from this one. So, what would cause that? Well, the answer is an impactor striking the surface at a very low angle, less than 15 degrees. And in this particular case, it seems like the impactor had already broken apart into three parts before it even hit the moon's surface. Yes, all three of these craters likely hit the moon at just about the same time, even the older crater. What actually happened here is that ejecta from this second crater likely fell directly on top of the other crater due to the low angle of the impact, which means that it has been artificially aged. There are some other really interesting aspects of this image though, like the solidified pond of impact melt found at the bottom of the crater, or this region here which appears to have caved in a bit. The impact melt in the first image also appears to have flowed down towards the left of the image. It really is a fascinating set of craters. Let's have a look at another asymmetrical crater and try to figure out why it has the shape it does. While it could be that this crater is also the result of two impacts, or one impactor breaking up into two just before it collided with the moon, scientists think that this is likely not the case here. Notice the shadows in this image, above and below the crater. It is apparent that this crater is right on the cusp of a peak. Zooming out and looking at the topographical map of the region reveals that this is the case. In fact, this may well have been the tallest peak in the local area until by chance this impactor came along and totally wiped it out. Imagine Everest suddenly being taken out by a meteor. The shape of this crater was probably not only caused by the angle the impactor approached from, but also because it hit this steep slope. It might not look that steep from the oblique angled shot, However, over only about 20 kilometers, there's an 8-kilometer difference in elevation from the peak here to the bottom of this nearby crater. In this next image, there's not too much to see. The only thing visible in this wide expanse is this peak basking in the light of the sun. Why is this significant? Well, this peak is on the rim of Apenus crater, a crater found near the north pole of the moon. Future colonies on the moon will be located somewhat near the north and south poles, because tucked away at the bottom of the craters here, where the sun never shines, are large pockets of water ice, essential for any colony to subsist off of. Water can be used for drinking, washing, cooking, and farming, plus breaking down the H2O into oxygen and hydrogen provides breathable air and rocket fuel. These poles also have the added benefit that there are peaks here that are almost always in the sun, unlike other parts of the moon, where the day and night cycle is 28 days long. 14 Earth days in constant darkness is not good for a solar-powered power system. A peak like this one, however, poking out in the sun while the surrounding area experiences nighttime, would be an ideal location for solar panels and powering a colony there. It's not a perfect solution, as peaks like this one will eventually also become covered in darkness depending on the time of year, but 89% of the time is definitely better than other regions on the moon where you'd get sunlight for roughly 50% of the time. While I'm at it, let's enjoy a couple more islands in the darkness, this time from the far side of the moon, found in Barbar crater. These are the central peaks found in the middle of this 80-kilometer wide complex crater. Islands in the dark are an appropriate way to end our exploration of the moon through the eyes of LRO. When it comes to space, that's all the moon is. That's all any astronomical body is. An island floating through a sea of blackness, sprinkled with stars. And yet, in these islands, such incredible beauty and wonders can be found. The LRO remains operational and will continue to run through 2024 and into 2025. As it carefully circles the moon across time and seasons, perhaps it will find new wonders, new craters and impacts from asteroids, or new rock slides caused by lunar quakes. The moon's surface is slowly evolving even now. And finally, once it has run its course and takes its last image, LRO will gracefully fall from orbit and will contribute to the history of the moon by creating one last crater. This small crater will not be as large as the Aitken Basin, but given the lack of wind or weather on the moon, it will likely remain there for millennia, a testament frozen in the regolith of the orbiter that did so much to map the moon's landscape for us. After all, by giving us this knowledge, it may just have paved the way for the first humans who will set foot on the moon and call its eerie, beautiful, crater-marked landscape home. Thanks for watching. If you enjoyed this supercut, be sure to check out my others in this playlist here. And a big thanks to my patrons and members. If you want your name added to this list too, plus a bunch of other perks, you can support the channel using the links in the description. All the best, and see you next time.